Hello everyone. Today I'm excited to present my works at ICPP 2025, Paracosm, a parallel framework for continuous subgraph matching. So nowadays, streaming graph processing has been used in many scenarios, like financial fraud, transaction detection, and the social network recommendations. So the streaming graph model is one of the basic models that used in graph processing. And so we are assuming that this is a graph that is labeled or unlabeled that keeps changing via a stream of edge or vertex updates. For example, the following figures is a graph model that shows simple batches of users. They are following relationships. And here, the A, B, C letters denotes the label of the vertex or the users. Now, if like some of the users, they start to follow others, in the graph model, we just insert the new edges representing the following relationship, and the delete means the unfollow relationships. So in these streaming graph processing scenarios, there exist algorithms for graph analytic that is continuous subgraph matching. So continuous subgraph matching incrementally identifies matches of a query graph, like the query graph in A here as an example, within a G data graph in response to each of the streaming updates. For example, we can take the example as we try to insert a new edges V4, V5 in the data graph, as the red line here shows. And here we can find that after inserting these edges, a new matches inside the data graph, that the label are all matches to the query graph, like V5 matches to U3, V4 matches to U0, V3 matches to U1, and V0 matches to U4, V1 matches to U2. The new matches increase. If we try to delete one of the edges, like V2, V3, then there is matches that disappear, as the red pattern here shows. So far, there are many existing CMCM algorithms, like the static subgraph matching methods try to rerun static subgraph matching for each of the updates, or some of the single-threaded CSM algorithms, they use some of the data structures to prune the search tree. And batches CSM and GPU-based CSM, they try to use some of the basic parallel technique. But for the most of the searching methods, single-thread continuous subgraph matching algorithms, they utilize the best of the data structures and try to prune the search tree most. But they are lack of multi-core utilizations. And although there are many kinds of CSM algorithms, they have a general workflow. First, they will input data and then do some of the offline preprocessing and do the online stream updating. So for inputting data, they will input the query graph and the data graph into the program. And then the program will store this data graph into some of the data structures like on order map. Then the algorithms has to decide the search or matching orders. For example, in this situation, I have to find the U0 at first, like finding some of the labels A inside the data graph, and then find U3. That means like for the labels A, its neighbors have to be also labels A, and then keep searching on. Another preprocessing technique is called build illusory data structures. So here, for example, if we see the data graph on the right, assuming that we are putting this data graph that has a new node called with label D. However, we didn't have a label D in the query graph. So here, the illusory data structures may help to prune the data graph with like unusable data vertex or the edges. And then on the online sections, will try to update the data graph with streaming. For example, here I just insert the new edges, and then the algorithm will try to convert the whole search process into a search tree. And here they will do the the tree traversal among the search tree and try to find the accurate incremental matches. And for the deleting the edge, the things goes familiar. One of the challenge of the CSM algorithm is that nowadays, in many real-world scenarios, people are using a big query graph instead of the small query graph. For example, in some of the companies' situations, they have to use query graphs that have 5 to 10 hops traverse. And they also have the big data graph. They are using like millions of vertices and billions of edges in some of the scenarios, like millions of users inside one of the apps or in some of the financial software. And our testing shows that in this situation, the existing single-thread CSM algorithms like Carnegie, Graphflow, NewSP, they got slower and slower after the big query graph size. Another challenge is for parallelizing CSM algorithms lies in two factors. First, the real-world CSM query graph cause imbalanced search tree. As you can see in the following example figure, if we use two workers to parallelize our CSM searching process, like worker 1 just trivially works on V4 subtree, and worker 2 works on V5 subtree. And then unlucky thing is that the tree is it has irregular workloads and cause the load imbalance across the threads. The second thing is that we find that the illusory data structures updating is a sequential process, which may not be parallelized in most of the CSM algorithms. However, we have found two key observations among the CSM algorithms and try to find some opportunity in parallelizing it. The first observation is that although we have to update the illusory data structures which may not be parallelized, the search tree process in online stream updating dominates the whole computation time. For most of the scenarios, like different query sizes and different algorithms, it contains about over 90% of the computation time, which shows that we can just parallelize find the matrix process and get a better acceleration rate. Also, this search tree exploration can be break into many subtasks, and their logic remains the same as the searching the root trees. The second observation is that we find that the safe update ratio inside the string CSM algorithms is very high. So what is a safe update? Take these examples on the left as an example. So if we try to insert edge V1, V4 in the data graph, and so this edge has the two vertex, that is C and A, but we only have AA, AB, BB, BC edges in the query graph. That is 5 edges, and none of them matches to these new inserted edges. So which shows that this insertion will not cause new matches. So this is a safe update. And we show that in most of the data sets and the query graph, the safe update is very high. And as the table shows, this is the unsafe updates. Most of the unsafe updates inside the datasets only contains like 1% of the whole update strings. So by doing that, we can try to merge most of the safe updates into batches to processing and increase the throughput of our system. So inspired by these two observations, we propose paracosms And you can see the main architecture of our paracosm systems has two executors. The inner update executors, which will parallelize the search process of the search tree, and the inter-update executor, which will try to merge different safe update streaming into batches and increase the throughput. So let's begin with some of the details inside the inner update. First, there is a master thread inside. You will start to search the search tree from the root. And you will try to increase subtrees as subtasks into a concurrent task tree. For example, in here, you find that you will have V5, V2, V4 as the subtrees or subtasks. Then, since we have 3 workers, assuming that we have 3 workers, you will stop when the subtasks are enough. And then you will come into parallel execution phase. Now we have 3 workers, and then they will fetch 3 subtasks by each from the concurrent tree. And then these workers will search with the original CSM logic, since this search tree has the feature that the subtask remains the same feature as the root task. Then we can find that if some of the workers they finish their jobs, as the figures on the right shows that the right subtree inside the search tree they have short heights and finish their jobs. Here at this time, you can see that the worker B on the left will try to push its low-level subtask into the concurrent tree. And at this time, the status shows that it is not some of the other workers is in Hungary, and they will try to fetch the subtask from the concurrent tree. So by doing that, the worker C and worker A will try to explore the rest of the subtasks. So by doing that, we can reach the load load balance by doing this work sharing technique, and find the ultimate matches inside one of the insertions. Well, another design is for the inter-update parallelism. And here, assuming that we have 5 workers to deal with 5 updates, and each worker will deal with the updates to see if they are the safe updates or not. They are using the classifier by using the label filtering. For example, if the edges don't have the label inside the query graph, or degree filtering, like the degree of one of the vertex is too small or too low compared to the query graph or candidate filtering. And then for the batch executor, they will do the parallel classification for different 5 threads. And if they find that all of the 5 updating, they are all safe, then they will continue to move on to the next batches, that is 6 to 10. But what if they find that one of the updating is unsafe? Then they have to explore this update string search tree to do the incremental matches. That is we'll handle it to the inner update executor to do the search tree explorations. And as for worker 5 for the update 10, since we don't know if the update is safe or not due to the number 9 updating, then the next batches will start from number 10. And by doing that, we can parallel classify and execute different update streams and do the coordination across the batches. So this is our inner update executor designs among 2 components. We also provide speed-up analysis of our paracosm systems. And for the details of the formula, please see our paper. Also, another analysis was based on why there are many high save update ratio inside the different data sets. So the whole process can be seen as we just randomly extract or find edges inside the data graph. So here, if one of the edges that matches to the data graph, the possibility is to that is the number of the label of the vertex square times to the number of the edge label, then divided by 1. So since QRegraph has like, for example, in this example, it has 4 edges, so the unsafe ratio may be like the number of QRegraph, that is 4, times to the number of the match, the possibility of matches. And for example, if we have a QRegraph that has 6 edges, then the unsafe ratio may be like 0.67%, and the safe update ratio is very high, which shows most of the updates are safe. And we also do the concrete experiments on setting up the Paracosm framework. We use 80 physical cores CPU with 160 threads, and we measure the computing time and the success rate. The success rate means the percentage of queries that completed within 1 hour. And we also use 4 different real-world data sets for the detailed experiments. And the result shows that for the overall comparisons, we use 5 CSM algorithms within single version and parallel version implemented by our Paracosm on 4 different real-world datasets: Amazon, our LiveJournal, our Bench, and Oct. That shows that Paracosm caused significant speedups across all algorithms and datasets with 32 threads. Like for GraphFlow, it will up to 30.2 speedup, and TurboFlux up to 9.5 speedup. And we also measure for the large query graph acceleration. So we can see that the right chart on the right table here, here it shows the success rate that is finished searching in 1 hour compared to single-threaded versions. And for most of the parallel version, Paracosm maintain effective gains for large queries. We also do the scalability experiments that utilize 8 threads to 128 threads of our systems. It shows that different algorithms all gain benefits with the number of threads increasing. And some other experiments are done for the loading balance in our inner-update executors. So the green dot here in the figure shows one thread computation time in the update streams. So you can see the balance for the balance load that has the work stealing implementation. The minimum execution time of one thread is like 15 seconds, while the maximum is like 25 seconds. But for the unbalanced load, that is trivially just let different workers to search the different subtasks at first and don't do any of the work sharing or stealing. For some of the shortest tasks, they just start like 1 or 2 seconds, then it ends. But for the other tasks, you all suffers heavy workload and cost 50 seconds to finish all of them. And we also test the benefit from the classifier, inter-update classifiers. So we test different type of the classifier that pruning the safe updates, the unsafe updates. And we also test the effectiveness of the interparallelism. Like for all of the algorithms, they reach higher execution time with the interparallel updates parallel classifier. So, in conclusion, we propose paracosm framework, an advanced parallel framework for continuous subgraph matching. And the paracosm leverages two kinds of parallelism, that is inner update parallelism, which breaks dynamic search tree into fine-grained parallelism with work stealing, and the inter-update parallelism that explores safe updates into batches that gets the updatation into concurrent updates. And the paracosm now has different tremendous speed up across various real-world data sets. And we now open source the paracosm on GitHub. So feel free to scan the QR code and experience the project. And thank you for your attention. And I'm now the fourth year of undergraduate students at SOSTech. And I'm now the past year was we spent the past year building the paracosm project, and I'm now looking forward to a PhD opportunity in the future. Thank you.